My name's Kyle. I'm really excited to talk to you today. First off, just wanted to thank all of the conference organizers, all of you. It's amazing to be back in person and kind of being able to do this live. I love it. Again, a round of applause for everybody who's been putting this conference together. So I'm going to basically be talking about WebAssembly, but in the context of an open source project that I've been working on and maintaining for the last 3 years called sqlc. Just by a raise of hands, how many people have heard of sqlc or are maybe using it in production? All right, that's more than I expected. I was really hoping maybe it was just going to be like one person over here, but really cool. What does sqlc do for the people in the audience who don't know about it? Basically, what it does, it's a command line tool for compiling SQL into type-safe code. In this case, it's going to be compiling it to Go. So let's take a little bit and kind of figure out how it works, right? So the first thing you do is you go ahead and you write SQL queries. The second thing is you run sqlc generate, which outputs that Go code basically with type-safe interfaces. And then third, you write your application code that calls those methods. Let's take a look at a quick example. So imagine you have an authors table, right? You have with 3 columns, ID, name, and bio, and you have one query that you want to execute, right? In this case, it's the get author query. It's going to return a single record from the database, and these are the kind of the 3 lines of SQL that you have to write. You take those 2 files, the schema file and the query file. sqlc will go ahead and read those, understand the query, parse the query, build up kind of the internal representation of that table, and then output a couple of different files. Specifically, it's going to output this query.sql.go file that has a basically type-safe method to give you access to that SQL query, right? So you can kind of see here that you can go ahead and call get author now, and that's Go, and it'll do all of the marshaling and all the scanning, and you didn't have to write any of that yourself. So sqlc has a bunch of cool features built into it that kind of makes it easy to write SQL. You noticed previously that I used a select star. You shouldn't be using select stars in production code, but what sqlc will do for you is that in the generated code, it'll actually expand the star into the set of column names that you have in your table, right? So if you add another column or something, your previous queries aren't going to break. It also has type inference built in, so you'll notice that we kind of had a parameter for that ID column, and sqlc is smart enough to know that that ID is a big serial in kind of Postgres land, and so that should map to an int64 inside of Go. And it also knows that if it's null or not and things like that. Lastly, and this is probably the best feature, is that it catches all of your typos. So if you've ever written a SQL query that's invalid, sqlc can go ahead and catch that before it ever makes it to your database. So one thing to note is that sqlc is a command line tool. It doesn't actually need access to your running database, so it's super fast. Some other advanced SQL things that it supports: common tables expressions, all of your favorite extensions that you use from Postgres or MySQL or SQLite. Again, has kind of type inference and type signatures for all of the built-in functions in the databases that you're using, enums, DDL, all of it. It currently supports Postgres and MySQL. It was originally written just with Postgres and Go in mind, and we have a beta for SQLite. Yeah, that was a lot about SQL because I hate to break it to you that we're actually at SQLCon now. This is SQLCon 2022. All of your favorite databases are here. We got Oracle, we got Postgres, we got MySQL. It's great. And so this is my SQLCon talk, right? Compiling SQL to type-safe code, HTML parsers, it's great. Okay, sorry, I get pretty excited about SQL, apologies. Let's get back to Go here, right? And talk about extending sqlc. So I open sourced sqlc in the beginning of 2020, and the basically feature requests immediately came in, right? I want to change some of the output. I want to add databases. I want to add programming languages. So for updating and mutating kind of the code gen output, you basically just have a configuration file, started small. Now there's like 30 or 50 options. It works okay. It's not great, but it's not too bad. Database engines are a little bit more complicated. So one of the best parts about sqlc on the Postgres side is that we actually use the real Postgres query parser. So there's never incompatibilities because it's actually the parser that Postgres itself uses. A big shout out to Lucas from PG Analyze. He's the one who's smart enough to be able to take that out of the Postgres codebase and wrap it in Cgo. I don't know how it works. It's amazing. What we're mainly going to be talking about today, though, is adding other programming languages to the output of sqlc. So very early on, we got requests for basically for Kotlin, for Python, TypeScript, C#, all of these other programming languages, right? And so the difficulty was, okay, how are we going to support other programming languages other than just Go, right? So let's talk a little bit about the internals of sqlc and how it works. So you've already seen this slide, right? SQL on one side, Go on the outside, right? How does sqlc actually work on the inside? It's mainly broken down to about 3 parts. We have the parser, the compiler, and then the code gen. Now, the parser, that's the one we talked about already, right? It has the actual query parser inside of it, takes your SQL and turns it into an abstract syntax tree that we then pass on to the compiler. The compiler says, okay, I'll take that, plus what I understand about your tables, what I understand kind of from the configuration file, and we'll turn that into a set of queries. The queries basically are the types of columns in your final output, and that gets passed over to the codegen package. The codegen package takes those queries and then generates the Go for those queries. And we're mainly going to be talking about that interface during today's talk. So this is where we started. This is basically when the code was open sourced. Again, it only supported Go and Postgres at the start, because that's basically what it was written to replace, basically all that handwritten Go code that you have in the database SQL package. So the original codegen package looked like this, had a simple generate method. That's where you passed in the queries. And then instead of writing out the generated files to the file system, it would return a map with a string, basically file name to file contents, right? So this was pretty good. The biggest challenge, though, was that it imported a ton of internal packages, right, to sqlc. So the plugin, basically that codegen package, just knew everything about sqlc. So it was really, really hard to kind of split the two, right? And again, it only knew how to generate Go, and it was written via text template. So it was kind of messy, and it wasn't like a great experience to kind of update that package. Now, when we talk about Go packages and kind of extending your program via Go packages, you can say, okay, well, we'll go ahead and throw an interface at it, right? So we had this generate function before, so create a generator interface that has that single generate method. And then instead of one codegen package, now we'll have 2 or 3, right? And that can work, right? And that's actually kind of what we ended up doing, right? And so if somebody wanted to come along and create a Kotlin interface or a Kotlin codegen output, they implemented a codegen package, opened up a pull request, and we merged it in. The problem was, again, all of that shared state made it that it didn't really implement a new package. They just kind of copy and pasted the previous one and then updated the templates instead of Go and making it Kotlin, or instead of Go making it Python. And so what that ended up basically happening was that all of the mistakes that I had made previously writing the Go code just kind of got translated over the Kotlin code and then merged and then became kind of my maintenance headache, right? As the sole maintainer, we just had this giant pull request, which is, here's Kotlin support. And I was like, sure, I think that's valid Kotlin. I don't know how to write Kotlin. And then basically here, 2 years later, I am now the Kotlin maintainer for sqlc, which is not super great, right? So we took a step back. I took a step back and I was like, all right, if I want to basically build out true plugin support in sqlc, I don't think going down with Go packages is going to be the best route. So what are basically the requirements for building out a plugin system for a tool like sqlc? First thing to remember is that it's a command line tool, right? So other users are running it in their own environment. I don't get to pick what software is installed on the host of basically the host environment. I have sqlc users across basically the board, so it has to support Linux, Mac OS, and Windows. And the last part here is, I think, also a little basically a little subtle, is if you're writing a language plugin, it's actually probably going to be best if you could write that language plugin in the language itself, right? So the fact that we're writing Go inside of Go is great because we get access to like the Go AST package, the pretty printer, the formatter. There's a ton of stuff. Writing Kotlin in Go, you don't have any of that. I'm sure there's some AST parsers and great formatters for Kotlin, but they're written in Kotlin. They're not written in Go, right? So we take those kind of for the context, and then here are some of the requirements basically for this plugin system. The first one is independence. And this is kind of, you can kind of think it also as being decoupled. We don't want to have to open up a pull request to the main sqlc repository to actually get this version of a plugin out. We really want people to be able to operate independently so that in the future, say if somebody decides to stop working on a language, it's a kind of bug report on a separate repository, not the main one. Another thing here is that sqlc's release cycles like every 2 months, and some people want to go much, much faster than that. The second one is safety, and in this case, we're going to talk about kind of security. You want to make sure that the plugins that you execute can't really do anything bad on your laptop, right? Especially if these are developer laptops, you might have some secrets or some type of, some important stuff on those laptops that you don't want people to steal or kind of destroy. This run anywhere one is actually really just about platform independence. If I'm a plugin author, I don't want to have to know about all of the different architectures the sqlc supports. I just want to write basically one that works on my machine, and then hopefully when sqlc adds support for new architectures, maybe Windows ARM or something like that, I don't have to go ahead and recompile or re-update my plugins. sqlc is a command line tool. You're using it day to day. It should be super fast, right? Just like the Go build tool and the Go toolchain is super fast, sqlc should be really fast as well. And lastly, if you're asking somebody to write a plugin for your system, they're going to have to learn how your system works. Don't make them also learn another system, right? Then they're just never going to want to write a plugin if they have to learn two things instead of just one thing. So let's take a look at how kind of the original Go package kind of scored on those requirements. Definitely wasn't independent, needed a PR. Was kind of secure because there was code review, but there was nothing like the Go runtime was helping with here. Run anywhere, you might think it's not like a success, but actually in this case it is, because sqlc itself is packaged for a bunch of different platforms. So if you've got code in there, you don't really have to think about how it's getting deployed to all those architectures. That's something that I deal with. It's super fast, it's written in Go, and if you're writing Go, it's already written in Go, very familiar, right? But again, not independent, and that's like the main thing that we're looking for. So what's next? If you go ahead and type plugin, Go plugin into Google, not the first result, but one of the third results is the official Go plugin package in the standard library, which I had never used before giving this talk before. It claims that 2,000 packages use it. I don't believe that. Could I get a raise of hands on anybody who's used this package in production? 2. Okay, that's what I thought. That's what I thought. So how does the Go basically official Go plugin support work? It's basically you pass a separate flag to the Go compiler, you output this basically SO file, and you can go ahead and open it using the plugin package, call lookup to load basically a function from that plugin, and then you can go ahead and execute it. So it looks a lot like the actual kind of Go package support, but it's at least independent, right? Like you can go ahead and compile it separately. You obviously have to figure out how to distribute that and kind of make it available to sqlc, but in theory, it should work. One of the biggest downsides, though, this is in the documentation, is it doesn't work on Windows. And I know there might not be very many Windows users here, but Windows users are a pretty significant portion of sqlc users, and we want to make sure that they can go ahead and use plugins. So that was a pretty quick kind of say like, oh, we're probably not going to be using Go plugins. It doesn't really help us on the security front, right? And when we talk about security, I want to specifically talk about what an evil plugin might try to do, right? So let's imagine that you're kind of a normal developer, right? Maybe you're working on you have an AWS account. On your laptop, you probably have AWS credentials somewhere. Maybe they're in the environment, in kind of the default environment variables. Maybe they're stored in the kind of default credentials location. We want to make sure that if you execute a plugin, that it's not able to see those credentials, basically steal them and send them off. This also isn't like some theoretical attack that's never happened. It literally happened like 3 months ago in the Python ecosystem. There were a bunch of packages that just importing them and putting them in like your main setup requirements file would basically then they would look for your credentials and try to steal them. So this is like the main thing that we're trying to prevent, is that we don't want people to be able to steal your credentials. So Go plugins, not going to get you kind of anything on the security front. Again, on the kind of the run anywhere, they're like Go programs. You're going to have to cross-compile them, right? So if we add a new architecture for sqlc or supported architecture, you're going to have to recompile all of your plugins. Now, on the fast front, I'm going to be totally honest, I did not benchmark Go plugins. I'm assuming they're written in Go and they're probably okay fast. I wouldn't classify them as slow, but I honestly really am not sure. The last thing is on the familiarity front. Yes, they're written in Go, but you have to use this kind of weird build mode. And I think a lot of people are probably going to be, again, there are only 2 people in this entire room that I think have ever used plugins. So Go plugin, let's go ahead and kind of throw that out. Next, let's talk about just executing and shelling out to a process, right? You would maybe like how this would work is that, okay, we have the sqlc compiler. Now, instead of calling a function, we're actually going to go ahead and basically define that interface using some protocol buffer messages or JSON messages, whatever you want, right? Serialize that request, send it over to a process over standard in. The process is going to go ahead and do what it wants, and then write its results out to standard out in a similar serialized fashion. This is, I think we've all probably used the osexec package to go ahead and basically shell out and call a command. This is basically just putting a little bit of wrapper over that. This is a really popular model, actually. If people are familiar with Proto-C, that's the protocol buffer compiler. This is how all of its plugins work, right? If you go ahead and they have to start with a special name, but it'll go ahead and look up the binary in your path, start the process, serialize that code gen request, have the process run it, go ahead and read it from standard out, and go ahead and write out the results. Now, the best part about this pattern is it's super well understood, right? We're just talking about like the Unix/POSIX model, right? Like you can do this in every single programming language, and most developers are super familiar with this, right? At the end of the day, you just have to print stuff out to standard out. The issue here is that, again, very independent, right? You can go ahead and deliver these binaries all you want. You don't get anything on the security front here, right? It's pretty scary today, but any of those Proto-C plugins that you're using probably could steal your credentials if they want to. Thankfully, they just don't. But like, just a good thing to kind of keep in mind. The same limitations when we were talking about the Go plugins. Your binaries have to be compiled for a specific architecture. You can't go ahead and just run them on any host machine. I would say in terms of speed, these are pretty good, right? Like, especially if you're calling out to another Go binary, you're obviously going to have some overhead in that serialization and actually starting up a full process. If you're calling out these plugins a ton, that's going to be a really big overhead, right? If you're creating all of these processes. There's a way, and we'll talk about a little bit later on how to basically amortize that startup cost. But right now in this kind of naive model, that doesn't really work. Last, though, on the familiarity front, I want to say I think this is probably the easiest way to basically have a plugin is that people and developers really know how standard in, standard out work. That's like kind of bread and butter for a lot of people. So osexec off the list, sadly not going to work for us. Let's go ahead and actually go to the first result when you look for Go plugins, which is not the official Go plugin package, but which is Go plugin, a package from HashiCorp. This is used in a ton of super successful projects, right? Terraform, Vault, Nomad, a lot of all of these projects are using HashiCorp's Go plugin package. Now, this looks a lot like the osexec model that we just looked at. The biggest difference is that instead of standard in and standard out, we're actually talking over gRPC. So HashiCorp that package will go ahead and spin up a process, open up a listener on gRPC, and it'll connect over the local network and go ahead and send those code gen requests and responses over gRPC instead of basically standard in and standard out. The biggest advantage of this is that it's a persistent process. So if you have some kind of long-lived background job, you're going to basically, you only have to have one process that gets spun up instead of many. And it's all kind of handled for you, right? Like Go plugin has a very opinionated view on how this should work, and you can go ahead and just use their SDK. Now, the problem is that basically opinion is a pretty large, I would say, complicated Go interface. And again, it's only in Go. While at the bottom, basically, it is just gRPC, and so you technically can write a Go plugin for HashiCorp in any language that supports gRPC. They only have an SDK for Go. So it's great if you write Go, and if you don't write Go, well, it's kind of not super great for you. I think it probably wouldn't take too long to figure out how to go ahead and implement this in a different language, but as far as I could tell, I haven't seen kind of anybody else do it. So obviously good on the independent side. Security, same thing, right? Those processes are going to have basically unfettered access to the network and to your local machine. I do want to call out one thing here is that in the README for this, they claiming that plugins are relatively secure. Relatively secure is a very scary phrase to see. They're not, right? Like they can go ahead and steal your AWS credentials, the exact kind of attack that we're trying to prevent. Same problem as kind of the other ones we've talked about. They're at the end of the day, they're Go binaries or any type of binaries. You're going to have to compile those for different host architectures. I would say on the fast front, the fact that you're kind of kicking off that persistent host, basically persistent process, means that it's actually the longer that process lives, basically the more performance you're going to get because you don't have to pay that startup process over and over again. The familiarity front, though, the SDK is really big. And so if this is, I think, the exact problem I was basically hoping to avoid, which was, hey, you want to learn how to use sqlc, first go learn this plugin SDK, and then you can come back and learn sqlc. So I will say in this one specifically, obviously it's not a bad choice, right? I think we've probably already all used one of the projects from, a few slides ago. Terraform has an ecosystem that is millions of times bigger than the sqlc plugin ecosystem will ever be. And I also think, especially if you're trying to run these plugins, say, somewhere else, actually on an environment that you control, you can easily use something like Firecracker or gvisor or some other kind of secure containerization to actually go ahead and make those plugins secure. So in this case, Go plugin probably not going to work. So let's just kind of go to something totally out of left field here, right? Like, let's just embed a scripting language into our Go process itself, right? Instead of, say, having an external process, we're just going to find a Go package out there that gives us an interpreter, right? This interpreter might be Lua, it might be Python, maybe it's JavaScript. But the idea is that we're actually just going to go ahead and have our plugin authors just write basically code, and we're going to go ahead and execute that code directly into an interpreter. This is how a lot of very popular programs do their plugins. If you've used Nginx, Nginx has a whole Lua scripting module, right? If you've ever used any kind of like 3D art programs like Blender, Blender has a huge Python, basically SDK embedded inside of it. So it really can work pretty well. One of the downsides of this, though, is that you have to make a lot more choices for your plugin users, right? You have to decide what languages to support. You have to decide what versions to support. And in case in Go, you have to decide which interpreter to use. It's pretty unlikely that you're just going to, say, use the default like CPython or the default Lua right off the shelf. You're probably going to have to go find some interpreter that is either written in Go or is in CGO and wraps an official interpreter to basically meet your needs. So that's kind of where the independence isn't as high, because your users really don't get a choice, right? You're going to say, here's Lua, and you go ahead and get to use the version of Lua that I picked. Security is also kind of all over the place. How secure is the interpreter that you pick? A lot of these interpreters maybe start off secure, but you can go ahead and say, oh, well, maybe you implement the OS package in Python, right? That's very similar to the OS package in Go, where you can go ahead and just execute arbitrary code. On the kind of platform independence, this actually is a really good option, right? Because you control the entire runtime. So that basically, scripting plugin that you've written, you can go ahead and just execute that inside of, in this case, it would be sqlc, and your users really wouldn't care what the host environment is. The speed of these is, again, kind of all over the place, right? Lua can be super, super fast. Python is not as fast as Lua, and JavaScript could be all over the place there, right? And it really depends on your choice of language, version, and interpreter. Lastly, on the familiarity, right? These languages are familiar to people, but they're going to be executing in a totally, completely unknown environment, right? You're going to be saying like, yeah, this is a Lua plugin that's run inside of my Lua VM inside of sqlc. You're going to have to do a ton of work here to really get that developer experience up to what I think most people would expect today if they were just, say, using Lua directly or Python directly. So I decided that the embedded scripting stuff was probably not a good fit for sqlc, and instead went with something called wasmtime. So there's been a couple of great talks here today and last few days about WASM WebAssembly, and I haven't seen wasmtime specifically mentioned yet, so I want to talk a little bit about what that is. So wasmtime, wasmtime.dev, is a fast and secure runtime for WebAssembly. It recently just reached 1.0, and it's been so far a really, really cool project to follow along. I will say, though, for a lot of people, you're probably like, okay, cool, secure runtime, great. What is WebAssembly, right? We've talked a lot over the last few days about WebAssembly, right? And I'm not going to be very honest, I'm not going to go super, super deep into exactly how WebAssembly works, right? And exactly kind of, the inner workings of it, because in our case, we really don't actually need to know too much about it. The biggest thing that we want to know is that basically it's a portable compilation target, right? So it can be one of those other, say, like one of our other operating system architecture pairs that we use when we compile Go to other different architectures. And the idea is that basically we can rely on compiler authors to go ahead and target what WebAssembly, and then us as basically programmers don't have to worry too much about it, as long as we have a runtime and a compiler that can output WASM. So this is actually from the most recent release of WASMtime. They wrote a big blog post, and literally the second big thing they called out in their blog post was using WASM for third-party plugin systems, right? My talk description said plugin ecosystem, and they wrote this, and I was like, great, I don't even have to write my talk. It's just WASM. Perfect. They even have this great little basically image over here that details kind of exactly how you would use WASM to go ahead and build out your plugin ecosystem. So it feels like we're probably on the right track, right? Again, released 1.0 very recently. All of the WASM code that you generate is platform independent, right? Because you're targeting the WebAssembly basically runtime. And so if in the future, say sqlc adds support again for Windows ARM, you don't have to change your WASM. The WASM will continue to work as it did in the past. The last thing here, though, I think it's the most exciting thing, which is that WASM, the wasmtime runtime, excuse me, the wasmtime is secure by default. So this is, I think, kind of new to, at least it was pretty new to me. I'm kind of used to like Go, a Go program can kind of just do whatever it wants as long as like the host lets it. But in wasmtime, it's the inverse. Your code can literally not access anything external by default. There's no file system access, there's no network access, and there's no environment variable access, right? Now, if it was just permanently none of these things, it might not be super useful for a lot of use cases, but it's a capability-based system, which means that at runtime, you can actually go ahead and grant access to your code to specific areas on the file system, to specific network addresses. And again, it's not all or nothing, right? So if you're executing WASM, you can actually say, hey, you can get access to this single folder on my host machine and nothing else. It's a really, really kind of cool programming model, and it's perfect when you're talking about executing plugins. The other thing here, though, is basically when we talk about WASM, it's really, really low level, right? I'm not sure if people here have looked at some other languages that target WASM directly. There's something out there called assembly script. If you look at assembly script, you're like, wait, where are the strings and the objects and structs, the things that I'm used to in a programming language? It's like literally functions and numbers, and that's it. And so when we take a look back at like how we're looking to build out our plugin ecosystem, we're talking about serializing structs across the wire. How are we going to basically expose that type of interface if it's only WASM, right? There's a few basically WASM only SDKs I've used inside of Go, and like the first 10 lines of the SDK are like VM runtime context, and like my eyes kind of gloss over, and it's like this seems a little bit too intimidating. So the good news is that I wasn't the only one that was a little intimidated by this. And another kind of sub-project from WebAssembly is this thing called WASI, right? And that's the WebAssembly system interface. And basically what that provides for WASM is things like file systems, files, network requests, and packets and things like that. And basically, you don't have to think about WebAssembly itself. You can just think about all the things you currently know: standard in, standard out, and reading things from the file system, and environment variable access. So when you could basically go ahead and combine those two, what you end up with is you end up with a codegen request, right, that looks very, very similar to the first thing that we looked at, right? You have standard in, you have standard out, you have, you basically, your code can go ahead and read those serialized messages in, and then write out to standard out, and that's it. But it's not a separate process, right? In this case, it's going ahead and actually running inside that main Go process from the start. So we basically have come full circle, right? We take all of the things that we like from kind of that process-based model and none of the downsides, right? So they're completely independent, right? They're not decoupled. They're not coupled to the sqlc kind of development cycle. They're completely secure. By default, basically sqlc plugins have no access to the network, to file systems, to anything, right? So there's going to be no sqlc plugin that's going to go ahead and steal your AWS credentials. The next one is basically on platform independence. As I said, you compile your WASM once, and then from there, it can go ahead and kind of run on any of the platforms that wasmtime runtime supports. Wasmtime is super fast. It was basically built originally to speed up operations in the browser. And so we're probably looking at a penalty of maybe 2 to 3, which is not too bad. And the last one, I think, on the familiarity is, yes, you have to understand, like, how do I compile my code to WASM? But if you're using, either in this case, maybe TinyGo or maybe Rust or another language that targets WASM natively, it's just basically a compiler flag. You don't actually have to think too much about your code. So that's what I basically decided on. Picked wasmtime. Was like, all right, let's go ahead and actually implement this. I was a little intimidated. It's like, okay, like a secure context runtime seems like it could be a lot of code. Actually ends up being pretty simple. So the first thing we start with is basically configuration. How are people actually going to go ahead and tell sqlc where their wasm stuff lives. It's really simple in this case. It's a URL or a directory path on the file system. We have a SHA just to make sure that kind of we can cache that wasm so we don't have to fetch it from the network every single time. So in this case, I'm defining a greeter plugin, right? In the next part, I'm saying, okay, well, instead of using one of the built-in CodeGen packages, we're going to use the greeter plugin, and we're going to generate its output into this gen folder on my laptop. So how does sqlc go ahead and use this? So load the configuration file, download the wasm if we need it. Go ahead and create what I call an execution context here. That's mainly using the wasmtime library to create an engine, take that wasm file, turn it into what they call a module, link it all up together, set standard in and standard out and standard error to files actually on the file system, and then just call the context, right? And then once that process finishes, it's very similar to basically OS exec. You're then just going to read standard out as well. Now, this is basically like when I first got this working, I was so excited, right? So the baseline, how fast sqlc was for a single project was around 30 milliseconds. And then I looked at like how fast wasmtime-go was, and it was almost a second. And I was like, oh my God, I just wasted like how much time? Like this thing is extremely slow. Why would anybody use this, right? It turns out it was like 27 times slower. And it's like, please don't take away that this wasm is 27 times slower. It's not. But let's learn a little bit about how wasm makes your code fast. So you basically compile to this wasm binary or file, and then wasmtime actually compiles that into machine code, right? So what was actually happening in that previous example is that every single time I was loading the wasm file, wasmtime was going ahead and compiling it to machine code and then executing that machine code. So wasmtime has basically a bunch of helpers to make it so you only have to pay that price one time. You can actually do it. You don't even need to run the code. You actually basically has forward or ahead of time compilation built in. So that previous step where we're actually downloading each wasm file, what we actually do is we go ahead, download it, then ahead of time compile it and save that onto disk, right? And then you can go ahead and load that module and it's ready to execute almost immediately. So when we go ahead and look back at basically the speed up here, we're going, in this case, it's not a second, right? It is a little bit slower, right? We went from like 30 milliseconds to 50 milliseconds, but still, I thought basically that was a kind of a good price to pay for all of the security and kind of that platform independence. So if you're looking for basically how to do this yourself, I don't have an off-the-shelf Go plugin replacement or anything like that, but you can actually go ahead and go to the sqlc repository. You can take a look at the wasm.go file, which basically does all of basically those 6 steps. It's like 260 lines of code, which is a pretty small amount of code, I think, for kind of getting the secure execution context. So that was where I was going to stop. But we need to talk a little bit more because this slide it's not technically true. So on the familiarity front, Go's built-in time, basically support for WASM isn't very great right now. It's targeted mainly at the browser, right? You can tell that with the Go OS JavaScript, right? And that WASM support does not support the WebAssembly system interface, right? Which is basically what we're relying on for these plugins. So as we kind of just learned, TinyGo is kind of the option that you pick, right? It's where you go ahead and go for WASM and WASI, except that TinyGo isn't Go, right? And so there are a bunch of things inside the TinyGo standard library that are in the Go standard library that aren't implemented in TinyGo. The biggest one is the reflect package. There's some parts of the reflect package that work, but a lot of them are stubbed out that basically just panic at runtime. So that means you don't get encoding JSON out of the box. You don't get encoding XML. And you don't get protobuf, right? And so in this case, if we go all the way back, we picked protobuf so that we could have basically the serialization format, but TinyGo doesn't support protobuf. Now, where do we go from here, right? Like, I am not a compiler engineer, right? And I was like, okay, well, I can try to get it to work in TinyGo, and I did. We'll talk a little bit about that. But where we ended up actually was, we're at GopherCon now, and maybe we were at SQLCon, but we're actually at RustConf now, and I hate to tell everybody, but I went ahead and wrote it in Rust. So, crustaceans and CodeGen, right? Building sqlc plugins in Rust. Hi, Kyle. So what actually ended up happening here, right? So you can go ahead and take a look at some of these plugins that are live on GitHub now. We have the Gen Greeter plugin, which is basically just Hello World, right? Again, written in Rust, goes ahead, compiled it to WASM, and you can go ahead and plug that into sqlc today. We have the TypeScript support for sqlc, which is finally basically in development. I was basically waiting for plugins to land before I was going to do this. This is also sadly written in Rust, but it's still a work in progress super early on. And I'm really excited to basically kind of get this out maybe in the next few months. So where do we go from here, right? Like it's a GopherCon, and you said I have to write this stuff in Rust. Let's take a look back at our kind of all of the plugin systems that we decided on and that we kind of jettisoned. And I do want to talk a little bit back about basically just execing and shelling out to a process, right? This is actually super flexible, right? And the biggest downside here is security, and as we said, kind of having to target individual architectures, right? And so basically what my thinking was, hey, if it's good enough for Proto-C, it's probably good enough for SQL-C, especially if the people who are writing those plugins are the people consuming them, right? We can be pretty sure that the code that we ourselves are writing probably isn't going to try to steal our AWS credentials and upload them to the cloud, right? And so you can actually go ahead and see one of these Go basically programs. It's currently it's in examples, it's inside SQL-C. And what this does is actually opens up almost, I would say, a third way to do kind of basically plugins in SQL-C, is that this just outputs that code gen request to JSON. And so if you don't want to worry about even thinking about protobuf, you can go ahead and use this, get a JSON output, and then whatever, however you want to consume JSON in whatever language, you can go ahead and do this. I kind of think of this as basically an escape hatch, right? Giving people the option to go ahead and write in a language that they love that doesn't have full support yet for WASI and WASM, which is totally understandable. WASM and WASI are like changing every single day, and there's like a million different proposals. So it's the bleeding edge right now, and maybe in 1 to 2 years, it's going to kind of like WASM time, I don't know, 4.0 is going to be super stable. But we are still kind of, I would say, in the early days. The last thing, though, I want to say is that process-based plugins are great, but I did not build in basically automatic distribution because that basically seemed like kind of remote code execution for me. So if you're going to use process-based plugins with SQL-C, you'll have to figure out how to get those binaries onto your hosts themselves. Whereas for WASM stuff, SQL-C will go ahead and automatically download it, and you won't have to manage it. So closing in kind of on the end here, I have 2 asks for the people, basically all of you Gophers who are watching this. The first one is to basically help me get serialization and deserialization of protocol buffers working in TinyGo. We're like really, really close. There's literally like one line, there's like a single reflect call in there that just needs to work. And it's like getting the package name for basically the package name from a file name. It's like, it should be simple. It's like so close, but I don't understand how reflect works at all inside of TinyGo. So please help me. And the second one is getting basically official WASM and WASI support inside the Go toolchain itself. TinyGo is an awesome project, right? I've written a bunch of like basically hacked together the protocol buffer support to get TinyGo to work. But I think it would be really helpful if we were able to get a officially WASM and WASI support inside the Go toolchain itself. So I'm not sure if there are any, say, Go toolchain committers in the audience today, but I'm hoping maybe my plea will go ahead and fall on the right ears. So that's it for my talk. Thank you so much.